Chemical process calculations, energy balance. Presentation by Group 2. Learning objectives. At the end of this lecture, students should be able to define energy balance and its importance, identify the key components of energy balance, calculate energy balance using the equation energy intake minus energy expenditure is equal to energy storage. Apply energy balance principles to analyze real-life cases and give a description of a closed process system. Simplify the energy balance and solve it for whichever term is not specified in the process description. Introduction. A system is termed open or closed according to whether or not mass crosses the system boundary during the period of time covered by the energy balance. A batch process system is by definition closed, and semi-batch and continuous systems are open. An integral energy balance may be derived for a closed system between two instants of time. Since energy can neither be created nor destroyed, the generation and consumption terms of the general balance equation drop out, leaving in deriving the integral mass balance for a closed system. The input and output terms were eliminated, since by definition no mass crosses the boundaries of a closed system. It is possible, however, for energy to be transferred across the boundaries as heat or work, so that the right side of equation 2.1 may not be eliminated automatically. As with mass balances, however, the accumulation term equals the final value of the balanced quantity, in this case the system energy, minus the initial value of this quantity. Equation 2.1 may therefore be written as understanding energy flows and efficiency. Energy balance in chemical processes is crucial for optimizing efficiency, ensuring equipment reliability, and minimizing environmental impact. This concept involves accounting for energy transfers, being net heat and work, within a system, ensuring that energy entering the system equals energy leaving it plus any accumulation within the system over time. Today, we will explore the fundamentals of energy balance, types of energy involved, calculation methods, and practical applications in chemical engineering. Overview of energy balance. Energy balance ensures thermal equilibrium within a system by accounting for all energy interactions. It is fundamental for understanding energy losses, designing efficient processes, and troubleshooting operational issues. Definition. Energy balance involves accounting for energy transfers, thus heat and work within a system. Its importance. It helps in maintaining thermal equilibrium, understanding energy losses, and designing efficient processes. Energy balance ensures that the energy entering a system equals the energy leaving it plus any accumulation within the system. It forms the basis for process design, optimization, and troubleshooting in chemical engineering. Types of energy. Heat, thermal energy transferred due to temperature differences. Work, mechanical energy transferred, such as through pumps and turbines. Chemical energy. Energy stored in chemical bonds. Example, fuels. Electrical energy. Energy associated with electrical currents. Understanding these forms of energy is essential for accurately assessing energy inputs and outputs in chemical processes. Each type of energy has specific units and characteristics that influence its role in energy balance calculations. The energy balance equation. The energy balance equation is foundational in chemical engineering. Energy in minus energy out is equal to accumulation, where energy in is the heat and work added to the system, energy out, heat and work leaving the system, and accumulation is the change in energy stored within the system over time. Calculation steps. First, define system boundaries and control volumes. Second, identify and quantify all energy interactions, including heat transfer and mechanical work. Third, apply the energy balance equation to each control volume. Fourth, solve for unknowns such as temperatures, heat capacities, and flow rates to achieve a balanced energy state. These steps ensure a systematic approach to conducting energy balance calculations. Engineers must accurately define boundaries and consider all energy interactions to achieve reliable results. Now, initial system energy is equal to final system energy is equal to energy transfer is equal to, where the subscripts I and F refer to the initial and final states of the system, and represents internal energy, kinetic energy, potential energy, heat transfer to the system from its surroundings, and work done by the system on its surroundings respectively. Equation 2.2 then becomes, or if the symbol delta is used to signify final minus initial. When applying this equation to a given process, you should be aware of the following points. The internal energy of a system depends almost entirely on the chemical composition, state of aggregation, being it solid, liquid, or gas, and temperature of the system materials. It is independent pressure for ideal gases and nearly independent of pressure for liquids and solids. If no temperature changes, phase changes, or chemical reactions occur in a closed system, and if pressure changes are less than a few atmospheres, then delta U is equal to 0. If a system is not accelerating, then delta E subscript K is equal to 0. If a system is not rising or falling, then delta E subscript P is equal to 0. If a system and its surroundings are at the same temperature, or the system is perfectly insulated, then K is equal to 0. The process is then termed adiabatic. Work done on or by a closed system is accomplished by a movement of the system against a resisting force or the passage of an electrical current or radiation across the system boundary. Examples of the first type of work are motion of a piston or rotation of a shaft that projects through the system boundary. If there are no moving parts or electrical currents or radiation at the system boundary, then W is equal to 0. Below is a solved example for studies. Example problem. Calculate the heat required to raise the temperature of a reactor by 50 degrees Celsius. Solution steps. Define system boundaries. Apply energy balance equation considering heat transfer, and then solve for required heat input. In this example, we will illustrate how energy balance principles are applied to solve practical engineering problems. This demonstration will highlight the step-by-step process and considerations involved in performing energy balance calculations. Applications in chemical processes. Energy balance calculations are integral to 1. Process design, ensuring efficient equipment sizing and effective heat management. 2. Process optimization, maximizing energy efficiency to reduce operational costs and improve productivity. 3. Safety, preventing overheating and ensuring stable operation of chemical processes, critical for plant safety. Energy balance calculations play a crucial role in every stage of chemical process engineering. They help in designing safer and more sustainable processes by optimizing energy consumption and heat transfer. Tools and software. Tools for energy balance calculations. Spreadsheet software for manual calculations and simple energy balance scenarios. Process simulation software for complex systems, providing detailed insights into energy flows and process optimizations. Online calculators, tools, and databases for specific energy properties and calculations, enhancing accuracy and efficiency in engineering designs. Engineers have access to various tools and software to facilitate energy balance calculations. These tools offer different levels of complexity and functionality depending on the needs of the project and the complexity of the process. Case studies. Real-world examples demonstrate the practical benefits of energy balance calculations, such as implementation of energy balance to reduce energy consumptions in refineries and chemical plants. Lessons learned from successful energy management strategies, emphasizing data accuracy and simulation validation. Real-world case studies demonstrate the practical application and benefits of energy balance calculations. They provide insights into how these calculations can drive significant improvements in energy efficiency and operational performance. Conclusion. Energy balance is foundational in achieving sustainable and efficient chemical processes. Mastering energy balance principles enables engineers to optimize operations, reduce environmental impact, and ensure process reliability. Energy balance is not just a calculation, it's a fundamental practice that underpins the success of chemical engineering projects. By mastering energy balance principles, engineers can contribute to reducing environmental impact and enhancing process reliability. Next, is a list of textbooks on chemical engineering thermodynamics that can be used as reference. Q. The end.